Good morning, everyone. I want to welcome you to another multivariate statistics class. Of course, today we're starting a new topic that we call inferences about multivariate means. Of course, this particular topic will not feature in midterm one. So what is going to feature in midterm one is what we did all the way to Monday. So what we are starting today is not going to be part of midterm one. So I want to welcome you once again to our new topic, inferences about multivariate means. Let me say this. When we talk about inferences, it's about testing hypotheses and constructing confidence interval. Okay. Of course, before now, I walk you through multivariate normal distribution. And of course, if we have more than one variables that are jointly normally distributed, we may want to test hypotheses about the values of a parameter, of maybe the variables simultaneously. Okay, so how do we test hypotheses in that regard? We can actually do that relying on multinormal distribution. So, like I said, once again, when I talk about inferences, about multivariate means, of course, it's more or less like we want to, test hypotheses about having more than one variable having a particular hypothesized value. So, or we want to construct confidence interval. I think I'm going to give us an example for us to really understand what this topic is talking about. So, the first example I'm going to give, okay, you know, in a stochastic environment, we normally have a claim. There's always going to be a claim. If a school make a claim um, about what the performance of students is in maths, okay, in maths, science, and reading, okay. Now, I'm actually seeing this as X1, I'm seeing this as S2, I'm seeing this as S3. They could simultaneously make a claim that the average, score in maths, okay, maybe under the H naught, they could say the average score in math is maybe 92, or they could claim that average score in science is 87, and average score in reading is 88. Okay, we can actually make this particular claim. Okay, now how do we test this claim simultaneously? Which means what is involved here is actually a mu vector. Okay, a mu vector is involved. So, and the mu vector is, so this is more or less like writing 92, 87, 88. Okay, so testing that the mu vector equal to that. Okay, how do we actually conduct hypothesis testing and stuff like this? Okay, this is what we want to talk about in inferences about multivariate means. And not only that, we may also want to construct a confidence interval, simultaneous confidence interval where we're going to have a confidence interval for this, for that at the same time. So when we're doing that, we're actually into making inferences about multivariate means. Another example, maybe we maybe there's a claim by maybe an administration in a country about the GDP growth, okay, the GDP growth, the inflation rate, okay, and unemployment rate, okay, and then unemployment rate. Okay, because we have more than two variables involved, you can see x1 or x2, x3. Okay, so we can simultaneously test hypothesis that the means of days, are equal to a particular hypothesized value. Okay, so this is applicable across all areas. Okay, even in pollution control, okay, where you talk about PM 2.5, talk about NO2, and you talk about CO2. Okay, now we may simultaneously want to test what's maybe they assume that the average of this equal to a value, the average of this equal to another value, and the average of that equal to another value. So with that, of course, we can conduct inferences about multivariate means. So which means we have more than one mean, okay? And we want to simultaneously test that the mean equal to an hypothesized value, not just one mean, but several means. Okay, do you understand our intention now? Now, since you understand our intention now, I'm going to go into the outline. How do we go about that? Okay, the outline has actually been partitioned into two. Okay, we actually going to consider a single mean vector. We're going to consider multiple mean vectors. Okay, so the single mean vector, this is an example of a single mean vector situation where this I'm assuming one setting. I'm assuming one setting for all of this. The other time I talk about a school, a school. This is happening in a school. But if I have several schools, that means I may want to compare the performance in math, the performance in science, the performance in reading. Okay, that will become a multiple mean vectors. Does that make sense? So that will become the multiple mean vectors where I'm actually going to perform a multivariate analysis of variance. But right now, what we want to focus on, we only want to focus on a single mean vector. This is a single mean vector, okay? Single mean vector. It is single because I'm considering one entity, a school here, okay? And it is multivariate because I'm actually looking into more than one subject. Does that make sense to everyone? So this is if you look at the economy one, like here, I'm actually referring to a single country. Okay, for me to perform a single mean vector, but if I actually want to compare the GDP growth, the inflation rate, the unemployment rate across countries, then I'm going to be considering multiple mean vectors. Okay, so in the single mean vector, of course, you're going to be introduced to that. I'm going to walk you through what we call the hotel link squared, the likelihood ratio test, the confidence region, and so on like that. And I need you to pay attention. Okay, I want to start with this inferences about a single mean vector. Like I said, this is a single mean. It's an example of a single mean vector. I'm only referring to an entity. Okay, I'm referring to an entity. So I just wanted to get that. I'm referring to an entity. Okay, now let's get started. You know, for you to be able to understand, okay, how we do this, okay, for you to be able to understand, okay, I need to first, we need to have a recap on how do we do this? How do we test hypotheses? How do we construct confidence interval when with where we're focusing on univariate? Because if you understand the way we do it in univariate, you will actually going to understand the way we're going to do it now in the multivariate case. So this is like we want to go back to what you've done before. Okay. Now I want to have a reminder on univariate. Now let's assume in the univariate case, in the univariate case, I'm only going to test this one at a time. I'm only going to focus on math or focus on science or focus on reading. That's a univariate, focusing on one variable at a time. Okay. Now, in the univariate case, okay, if we have that, x1 up to xn, for the normal distribution, so we're actually going to take a sample size from, distribution. And of course, we realize, oh, it is normal. Okay, it has to be normal. Okay, so, and that's why you see that, for univariate case. Now, in the univariate case, I know you've had about one sample t-test. The one sample t-test, if I want to test, the performance, if a school make a claim that the average performance in maths is 92, okay, all what we just need to do is to go to the school and take a sample of score in maths, okay? And that is what we're actually going to apply what we call a one sample t-test, okay? The one sample t-test is parametric. It's a parametric test, It's a parametric. Okay, it's parametric. Parametric in the sense that it relies on assumptions of normality. Okay, it relies on assumptions of normality. So what we're trying to say here, okay, so what we're actually saying is that okay, the score in math follow normal distribution. Okay, with the mean of that mu and the variance sigma squared. Of course, you know how that can be investigated. If you have a scores in math, you can construct the histogram to be able to see. You can generate the density plots for you to be able to see. You can conduct a Shapiro-Wilkie test of normality, or you can conduct an Dancy test, a different kind of normality test, for you to be able to see whether they follow normal distribution or not. Okay, so if the score in math that I just talked about follow normal distribution now what do I want to do? What I want to do is suppose the variance is unknown, because let me tell you this, we got different kind of t-tests, okay? And this is what happens when the sigma square is known, okay? When sigma squared is known, we use a z-test. I'm going to say that again. When sigma square is known, we use a z-test, z. Has anybody heard about z-test? Have you heard about z-test? When sigma square is known, we use a z-test. When sigma square is unknown, then we use a t-test. Now, when the sigma square what I'm talking about here is a population variance. Population variance. Now, if a sigma square is unknown and we want to test this, what are we testing now? We're testing under the null hypothesis that mu equal to mu naught, and it gives me now equal to mu naught. What we're trying to say here, maybe we're testing that, okay, maybe a school make a claim, and of course, investigation is going to follow a claim. So if a school make a claim that, okay, the average performance in math is 92, okay, mu naught, the mu naught there is going to be 92. So which means I want to test that. Okay, if I really want to test that, okay, like I said, I'm going to use a t-test. I'm talking about univariate case. Now the test statistic is going to be that. Okay, that's going to be the test statistic. Now, if that is the statistic, the X bar is going to be the sample mean, which is going to be the average score of the student, because you're going to go to this school to choose a sample of score. You find the average, that is going to be called sample mean. And of course, the mu naught is an hypothesized value, which is going to be the claim of the school. Okay. And of course, S is the sample standard deviation. And of course, if you want to figure that out, this is the formula, for the mean. This is the formula for the sample variance. If you take a look at it, the formula that we have here, of course, you already, you're familiar with them. Now, we understand how this is achieved under when univariate case. But you know what we want to do now? We want to have a way to extend the univariate case to multivariate case. Instead of force to test one mean at a time, we actually one mean of one variable at a time. We want to extend that to multiple variables. Okay. If we want to do that, please, I need you to pay attention. Of course, in the conventional t-test, when I have a test statistic value, of course, if test statistic value is large, I'm likely going to reject the null hypothesis. When the test statistic value is large, the p-value would be small. I'm going to say that again. When T is large, when test statistic value is large, the p-value is going to be small. When p-value is small, you are more likely to reject the non-hypothesis. But and that's exactly what I'm trying to talk about here. Okay. But you know what? Because I actually want to extend the t-test, the one sample t-test in the univariate case to multivariate case, and I'm actually going to use an approach that we call Ortelin t-squared. What I'm going to do, can I have a way to square my t? If you come back here, I want to square this guy. I want to square t. Okay, it's like what I actually want to do. Okay, I want to square this guy. When I square that guy, it's gonna be squared. Okay, that's gonna be squared. This is gonna be squared. Okay, and of course the square root of n is also gonna be squared. Okay, now we want to square each of that. So while we squaring each of that, we actually want to extend univariate test to multivariate test. So when we do the squaring, okay, please, I need you to pay attention. Math is easy when you pay attention and you understand what is behind the scene. Now you know what I've done here. I've already squared, and when I squared, I rewrite because the square root of n is going to be n. Okay, when I square, and square, this is more or less that is being squared. When I have x bar minus mu naught, another x bar minus mu naught, it's like I have an x bar minus mu naught that is squared. And initially, um, I got x here, right? I got x here, right? When it is squared, it's gonna be x squared. Initially, it's occupying the denominator position that I want every one of them. I want the denominator. I want to collapse the denominator. I don't want a fraction anymore. I'm bringing this guy up. I'm bringing that guy up. When I bring x squared up, I'm actually gonna get this. Is there anyone in this class who doesn't understand this? Is there anyone? Let me tell you this. The midterm two test we're gonna base on this majorly. And that's why you have to I needed to, if you don't understand, ask question. Okay. Now t square equal to that. Now, if you look at the way it is written now, we want to project, we want to write this in a multivariate form, and that is why we are actually writing it in this way. Now, and if we're able to do that, our decision will no longer be based on T. You remember in the univariate case, we base our decision on T, on the test statistic value, right? But right now, it's not going to be based on T, but it's going to be based on T squared. Now, when you take a look at what I have, when t squared get larger, what can make a t squared to get larger, okay, is when the x bar minus mu naught The X bar minus mu naught is the distance between the sample mean and hypothesized value. Okay, when that guy get larger, for when you fix the variance and sample size, okay, then the t-square is gonna get larger. And I think I've gave another reason why t-square is gonna get larger. Why am I interested in t-square getting larger? I'm interested in t-square getting larger because that is when t-square get larger is when the null hypothesis can be rejected. Does that make sense? Okay, now working on that now. Okay, now based on where we are now, we've been able to write a t-squared. Okay, now we now want to extend that to multivariate case, so to situation where we have more than one variable. Okay, and if we want to start, you remember the other time, okay, when we started the univariate case, okay, when we started the univariate case, I actually said my xi is from a normal distribution. If I also want to start my multivariate case, I'm also going to say that, take a look at what I have right now. Okay, what do you think I said? SI. The SI. Okay, SI mean I have S1, X2, S3 up to XP. Follow multivariate normal distribution. The mu that you have is actually going to be a vector mean, and that sigma that you see is actually going to be covariance matrix. And as you're looking at them, one is a population mean vector, the other one is a population covariance matrix. Does that make sense? Now, this is trying to just tell you, oh, xi, x1 up to xp. Oh, maybe I'm talking about performance, school performance. The x1 may be math, performance in science, performance in reading, and so on like that. Then they are going to have their population mean. Okay, and at the same time, there's going to be a covariance matrix for that, where I'm actually going to have opportunity to have the variance for each of the variable, and also to be able to have the covariance between them. Now we're getting there. We are getting there. Now take a look at that now. Suppose you remember the other time under the univariate case, I also started, I said, suppose sigma square is unknown. Okay, you know when I say sigma square, I mean population variance, but I only going to talk about population variance in a univariate case. I'm going to say that again. I'm only going to talk about population variance in a univariate case. But in a multivariate case, I'm not going to talk about population variance, but I'm going to talk about covariance matrix. Does that make sense? Covariance matrix. So the covariance matrix will replace sigma squared. Does that make sense? Now, if you look at the my hypothesis formulation now, my hypothesis formulation now, it's not just it's a mean for one variable. Okay, we got mean. That's a mean vector. Does that make sense? That's a mean vector. Is there any question on that? That's a mean vector. So now the next thing is we need a t-squared. Now I need you to pay attention. Okay, I need you to pay attention. Now the other time from the t-squared, this is what I have from the t-squared. And you know what I'm gonna do? If I want to translate that, if I really want to translate this guy, give me 1 second. If I want to translate this guy into multivariate right now, that a lowercase t squared will become an upper t squared. That is gonna become this guy. Can you see that? So this guy is gonna become that guy. N is going to remain N, right? N is going to remain N. And this guy is going to remain that guy. But here, I need to put a transpose. I need to put a transpose. And, oh my God. You have a S squared. What's going to replace S squared is going to be that. You see that? It's going to replace that. Now, and with that now, with that replacement, can we see what do we have at the moment? Okay, what do we have at the moment? Now, what we have at the moment is this guy. Is there any question about that guy? That's what we call Otelinti squared. Okay, Otelinti squared. Okay, that's what we have right now. And that very S, some of you may be wondering, let me do this. You know, here, you see, I have S squared. Um, we're using this is sample variance. In the univariate case, we say this guy, population variance, is unknown. If population variance is unknown, we're going to be working with the sample variance. Okay, that's why you see S squared. S squared is the sample variance. Now, the same thing in the multivariate case now, okay, in the multivariate case, okay, this guy is unknown. If this guy is unknown, if the population covariance matrix is unknown, then we're only going to settle for what? For sample covariance matrix. So the sample covariance matrix is X. Is there any question? So the X that you see is the sample covariance matrix. So if I want to compute my t-squared, because if I want to conduct this hypothesis right now, okay, if I actually want to test this hypothesis, the HO against H1, then I actually need a test statistic, which is going to be a t-squared. And how am I going to go, computing the t-squared? Of course, I know what my n is. That is the number of observation. Then the x bar is the sample mean vector, which means I'm actually going to come to this school. Okay. I'm going to take a sample of score in maths. I find the average. Take a sample of score in science. I find the average. I take a sample of score in readings. I find the average. That's going to be x bar. Okay. Now, the mu naught will be the hypothesized value, the claim of the school about the performance. Does that make sense? And of course, the S is the sample covariance. Of course, so this is the formula for the mean, this is the formula for the sample covariance. Is there any question? Okay, now, before now, actually, when you want to work with matrix, right? When you have a data matrix, right? When you have, like, if you don't want to go by way of, if you don't want to go by scalar computation, this is like scalar computation. But if you want to go by way of matrix, of course, before now, you remember when, when we're dealing with that data matrix, of course, I walk you through all of that, how you can obtain your mean vector, how you can obtain your sample covariance and so on, like that, and now you can do the centering. Okay, now I need you to pay attention now. We know what our t-square is, but in statistical analysis, if I want to conduct hypothesis testing, okay, then I need to be able to understand what is the distribution of the test statistic. I'm going to say that again. When you are conducting a t-test, the distribution is t-distribution. When you are conducting an f-test, the distribution used is f-distribution. Why do I need those distribution? I need those distribution to figure out the p-value, because the p-value is what I'm going to use to take a decision on whether to reject the non-hypothesis or not. So if I actually conducting a statistical hypothesis testing, okay, I need to be able to understand what is the distribution of my test statistic. Right now, the distribution of a t-square now is f. I need to is follow a scaled f. Okay. the distribution of t squared now follows that. A scaled f. Okay, why is this called a scaled f? Because you can see a weight. We use this guy to multiply f. The f distribution with two freedom, p comma n minus p. Okay, now if I want to take a decision using the p-value, okay, then I need to be able to understand what is the distribution of my test statistic. This is synonymous in the court of law. Before you can seek for justice in a particular court, then that very court must have a territorial jurisdiction, which means, okay, you are being tried in a court where the incident happened. This is around, it's just like somebody break a Minnesota law. It is expected that the person should be tried using Minnesota law. So which means court in Minnesota has a territorial jurisdiction for that. That's what we mean. Now, in hypothesis testing, okay, it is very crucial, the distribution of your test statistic. So right now, the distribution of a t-square is a scaled L. Take a look at that. That's a scale L. Okay, and what are we going to do? So what we're going to do is, okay, when t-square is bigger than that, okay, we're going to take a decision. So which means your alpha now, okay, your alpha, which is the level of significance, okay, alpha is a level of significance, which is also the maximum probability of committing type 1 error is going to be equal to the probability of a t-squared greater than the scale f. Okay, if you want to figure out the p-value, don't forget the p-value is the probability of observing an extreme value when the null hypothesis is true. Okay, and of course, that can also denote what I call the upper 100% percentile of the F distribution. Now, where do we reject? Please pay attention. Okay, of course, we are focusing on situation where t-square is large. When t-square is large, that will call for rejection. And how large is the large? Then the t-square must be greater than this guy here. Please pay attention now, which means I need to first have an F value that I'm going to check from table. Then I'm going to multiply it by this. You know what your n is? Your n is the number of observation, okay? And your p is the number of features, the numbers of predators, okay? So this is condition under which we reject the non-hypothesis. We reject the non-hypothesis when t-squared, okay? And don't forget, we're out to find your t-squared. This is how to find your t-squared. You see that? You find your t-squared from there. When you find your t-squared from there, then you're actually going to compare with what you check from the table. Well, you check this guy, we're going to check this guy from the table of F. Okay, when t-square is greater than that, then we're actually going to reject the non-hypothesis. That is how we use Ortelin t-squared, okay, to conduct hypothesis. Now, I want to play, I actually want to I want to compare student t-squared because the conventional t-test in the univariate case is actually called student t-test. Okay, now if I want to compare student t-squared with the Ortelin t-squared. Ortelin t-squared is what we use in a multivariate case. I'll take a look at this. If you look at this guy now, if I call this one the Ortelin t-squared and this one the t-squared, the only difference is just like in this side is multivariate vector. Of course, the sample mean is going to be a sample mean of vector. The hypothesized value is also going to be a vector, and that was why I call this part a multivariate normal vector. Okay, and of course, the distribution of this guy, okay, is going to be Wishart. I said that the other time, it's going to be Wishart. If I compare that with the univariate case, the t-square for univariate case, of course, this guy is going to be just univariate, just one sample mean, one hypothesized value, and this distribution is going to be chi-square for the variance. You remember in the univariate case, the distribution for the variance is actually going to be chi-squared. So this is comparing, the student t-squared with the Hotelin t-squared. I'm actually going to say they are different in terms of the numbers of variables. One focus on one variable, the other focus on many variables, and of course, the distribution is different. The distribution of the variance in each is different. For the multivariate case, it's Wishart, and for the univariate case, it's a scale chi-squared. Okay, now you may be wondering if you go back to this how you conduct a t-test. I mean this the Hotelin t-square. The other time I show you the formula, I show you how to take a decision. And if you want to do that in now, this is the code that I supply here. I will advise that you run this code. Okay, that is the code. If you know your data X. Okay, if you know your data X, your code is when you run this code, it's automatically gonna generate a result. Okay, this is giving a real life example in R. Okay, the real life example now, if you take a look at this, we're using a data on empty cows. We got variables like MPG, DISP, HP, WT. Okay, so this is how we perform the Hotelin t-square in R. Okay, take a look at all of that. And at the end of the day, you're going to use the p-value to be able to take your decision. Okay, so we have so many other ways to do that. As I'm showing you right now, so many other ways. Okay, you can read the code. Okay, I put the code for you to run the code in case I give you assignment. But you know what? Because of my time, I'm actually want to go into multivariate normal MLE. Of course, when we were working with multivariate normal distribution, I walk you through how to estimate parameter in the multivariate normal distribution. I think we did that on Monday. Of course, if you want to do that, you need to first start with the normal density, or you write the likelihood, you write the log of the likelihood. So this guy is a log, the logarithm of the likelihood. And of course, that is what I'm going to differentiate with respect to mu and with respect to the variance covariance, set it to 0, and that will give me these two results. These two are called the MLE. If they ask you to find an MLE of mean, MLE of variance covariance, now I need you to pay attention now. The difference between MLE, okay, if you take a look at it, for mean is the same. Find your sample mean. MLE, the sample mean. But for the variance covariance, if you take a look at the MLE here, you're actually going to see this is divided by n, right? But in the case of sample variance, is divided by n minus 1. That is different. Does that make sense? Okay, I'm going to take you back. Let me take you to sample covariance. Give me 1 second. You're going to see something now. Sample covariance. I'm going to go up. Take a look at this. What do you see? This is sample covariance. That is not an MLE. This is not an MLE. Why is it not an MLE? It's divided by n minus 1. But for MLE, just divide by n. Does that make sense? That is a difference. Okay, that is different. We're talking about MLE. But I think I gave you in the assignment, right? Let's take notes. So the MLE for the mean remain the same, just the regular mean. But the MLE for the variance covariance is not the same as that of the sample covariance. The only difference is in one, you are dividing by n, okay, by the number of observation. But in the other one, you are dividing by the number of observation minus 1. Okay, now, if you, now, let me prepare your mind. I actually want to develop another approach for testing hypothesis here. I've already showed you the Hotelin t-squared. Hotelin t-squared has some challenges, has some limitations, and that's why We got more than one technique of conducting hypothesis in multivariate setting. Now, you know what I want to do now? I actually want to develop a brand new approach, but through the process of maximum likelihood estimation. Now, from the log likelihood that I'm actually showing now, when I differentiate with respect to mu and I set to 0 and I solve for mu, it's going to give me this guy. When I come back and differentiate with respect to the variance matrix and I set to 0 and I solve for that, I'm actually going to have this. So these two, they are the maximum likelihood estimate or estimator. They were derived by optimizing the log likelihood function involving multivariate normal. Okay, now after that, you know what I'm going to do? Please pay attention. Please pay attention. Do you know what I'm actually looking for? Using the method of maximum likelihood, you know what I'm looking for? What I'm actually looking for is this. I want a situation whereby I'll be able to maximize the mu vector and the covariance vector. That's what I want to do. I want to maximize the mu vector and the covariance vector. Okay, that is exactly what I want to do. Now, I need you to pay attention now. I need you to pay attention. If I plug in the values, please pay attention. Pay attention. It's mathematical. What I got here. What I got here. Wherever I see mu, wherever I see this guy, wherever I see mu, I want to plug in, this guy. Wherever I see this, I want to plug in this guy. Wherever I see them in this log likelihood function. Wherever I see mu, I want to plug in that. Okay. Well, wherever I see mu, I'm going to plug in S bar. Wherever I see mu, I'm plugging in S bar. Wherever I see covariance, I'm going to plug in that guy. When I plug that in into this equation, I'm plugging in this guy and this guy into this equation. It's actually giving me this. It's going to give me this mathematically. It's giving me that. After plugging that in, you can try that. Please try that. I'm going to say that again. I'm going to say that again. Try that. I needed to try that. Okay. We are plugging in wherever you see mu. I'm plugging in X bar. Okay. Wherever I see this, I'm plugging in this guy. I'm plugging them into this equation here. That's what I'm doing. When I plug them in, and I simplify, okay, okay, I'm actually going to have this guy here. I have this guy here. Okay. Now, when I have this guy, I believe, do you know my belief right now? My belief is that this guy, okay, in this expression, then I've been able to maximize my mean vector and I've been able to maximize my covariance matrix. Does that make sense? Now, I needed to pay attention to this guy now. When we want to test hypothesis, okay, when we want to test hypothesis, okay, the hypothesis that we want to test is mu equal to mu 0 or not? You know what we're going to do? Okay, we're going to come here. We're going to come here. Okay, if I want to test whether mu equal to mu 0, okay, it means if wherever I see mu, I'm going to plug in mu 0. But right now, there's no any mu, right? Is there any mu? There's no any mu. Look at the expression. Do you see any mu in the expression? Okay, no. But the only thing I can see in the expression is a covariance matrix. So what I can do is to plug in covariance matrix 0. Take a look at this. What is the difference between this and this? I have plugged in covariance matrix under the null hypothesis, under HO. That's why you see sigma O. Does that make sense? Assuming the null hypothesis is true, okay? Because you know why? there will be mean vector for HO, there will be mean vector. For alternative, there will be covariance matrix. For HO, there will be covariance matrix for H1. Does that make sense? Now, right now, what am I talking about? Okay, please pay attention. Okay, pay attention. Okay, now that from here, now I got this guy, right? Now, if I got this guy, now the question is, here, is if I know my N, I know my P. The only thing that I need to figure out is this guy, right? Is the covariant. Now, which is going to be this guy. I'm going to use this formula here. What am I using? I'm using the maximum likelihood formula. You can see divide by N, right? And where you see mu, what do you see? Mu naught. Because this is the covariance for as that is assuming the null hypothesis is true, and that is why it has a subscript 0. Then the mu is also going to have a subscript 0. Any question on that? Okay. Now I need you to pay attention. Oh my God. I'm also going to do the same for the alternative. I'm actually going to do the same for the alternative. You know what I have here? What I have here now. If you take a look at this, what I have here now. That is for the HO. For the H1, I'm just going to assume sigma, not sigma 0. Does that make sense? Because the alternative is going to say it is not mu naught. If it is not mu naught, then the covariance, if I have a sigma subscript 0 for the covariance for HO, then the one I'm actually going to have for the alternative can just be just sigma. And when I have that, okay, which means I'm going to have two different one. And if I have two different one, you know what I'm going to do? I want to find the ratio. Please pay attention. I needed to see what I'm doing here. What do you think? You know where I'm going? Because the approach that I want to use is a likelihood ratio test. In the likelihood ratio test, if you look at the numerator is the maximum likelihood expression when the null hypothesis is true. The denominator when it is not true. You can see in the denominator, what do you see? You see mu, right? Okay, in the numerator, you see mu naught, right? Now, if I do the ratio, if I do the ratio, something is going to cancel out. Okay, I need you to take a look at this. If I do the ratio, okay, this exponential raised to power that and 2 pi, whatever, we cancel out. You know what I'm going to be left with? Oh my God, I'm only going to be left with this guy. I'm going to be left with that. That divided by that. That's what I'm going to be left with. Which means, you remember what we did before? Generalized variance. That is a ratio of two generalized variance. The generalized variance, the H naught is the generalized variance, assuming the alternative is true. Then the bottom one is the generalized variance, assuming the H naught is true. Okay, you know what I'm going to do? I'm going to continue from here next time. You know what I'm deriving? I'm actually deriving what we call weak lambda. Weak lambda is a likelihood ratio test approach to, to conduct a statistical test of mean in multivariate analysis, which is a little bit more superior compared to the Otterlington square. Is there any question? You can see what we're relying on. We've been relying on the matrices that we did before. Okay, this is where I'm going to stop. We're going to continue from here next time. Make sure you stay safe and have a lovely day. Bye for now, everyone. Yeah, how are you? I'm good.
What does it mean to maximize the mean vector finding? Are we talking about max likelihood in terms of like positioning within the PDF?
Okay, what happened is the method of maximum likelihood
Mhm.
is about proofs. to estimate parameters from a normal distribution. If I have data set and my data set follow normals, then I need to, before I can make whatever I need, then I need the mean and the variance. So if I'm using the method of maximum likelihood, the method of maximum likelihood is going to say, okay, I want to obtain the values of a parameter where the likelihood is going to be more. The likelihood that is going to be that, the likelihood that the chance that that is the true parameter of interest. That is the true value of parameter of interest.
So what we're maximizing is the area under the curve.
Exactly.
Okay.
You're maximizing the area under the curve. You're maximizing the probability, the chance.
Gotcha.
Of that. Yeah, exactly.
Wonderful.
Yeah. And that is why we're using probability distribution. So
right.
We started from normal distribution and we write the likelihood function for it, and that is what we optimize.
Gotcha.
Yeah.
Okay. And then I got comments back on my previous assignment. Thank you so much for the return with that.
Oh, you get a comment now?
I have comments from the TA. Yes.
Right?
Yes. Thank you for that. I do have a couple of questions about their comments. In some classes, the TA just does grading. Is it appropriate in this class for me to reach out to the TA directly and say, hey, let's meet and talk about these comments? Or would you rather I talk to you about the comments?
No, you first reach out to you.
Okay.
You decide the right to ask questions. So yeah, you pay for the service.
Awesome. Thank you. Thank you.
About the last assignment.
Yeah.
I think the both question to be honest. Like, are you grading this one?
No, it's my TA grading.
Oh, well, actually, like I wonder, do I have the opportunity to do something one because this is 3.6. I think 3.5.
Okay, so what you can do is
I emailed
you
TA.
send it to two of us. I'm gonna wait when TA does something. When he doesn't get, then I'm actually getting.
Okay, so I send you an email and CCTA.
Yeah, send to two of us together at the same time. Send to TA, copy me.
Okay, sure.
Yeah.
All right, thank you.
Yeah, you're welcome. Yeah, how are you?
Good. How are you?
I'm good.
So, we were planning on participating in a hackathon.
Professor, it's called Minimodac 2025. We were wondering if you would consider being the mentor for our team.
That's no problem. I'm flexible. Yeah.
We'll reach out via email.
Yeah, I'll send you the details.
Okay, I'm going to be expecting that.
Okay.
Hello. How are you doing today?
Pretty good, actually. I'm feeling pretty good about the next homework, but I just had a quick question about the quadratic function. I haven't taken that. So I don't know what that formula is gonna look like.
Which one?
So it's just a bivariate normal, and then they ask to do like the density.
Right now, the square statistical distance expression as a quadratic function. Yeah, this is this is more or less like a quadratic function. The quadratic function is going to be
Yeah, I think I saw what it looks like, but I
Yes.
just wonder how I can translate the two equations.
I can. Yeah, what I just trying to say is after you work this on data, it's going to be a function of x1 and x2. That's a quadratic function. But you know what's going to happen? The x1, the x2 is going to have something squared.
Okay,
So
so just
quadratic
fix.
is going to be squared.
Right.
So
Okay.
the moment you just apply that on data,
Mhm.
and it's going to be in terms of x1 and x2, you will see that,
Okay.
oh, this is looking quadratic
Okay.
nature. So that's all.
That's
it is.
fine. Okay, thank you.
You're welcome.
About like 4052 for this week's assignment.
Yeah.
I think the question one, we need to perform a for
Autoflow selection.
selection. Yeah. And for the question, we need to like